welcome to What Makes It Tick. Got me a nice cup of coffee here, sat down to do some learning. What we got today is a pair of Magnatech Universal Watt Reducer Slimline lamp ballasts. Did these on a change for a store. They had the long T12, what was it again? The two F96 T12 fluorescent lamps up in the ceiling for lighting in the store. And they had two lights that weren't working. So I went in, changed bulbs, all this, and finally diagnosed it as the ballast. What that ballast does is it takes 120 volts at 60 hertz and steps it up to a voltage and current that those bulbs use. In this case, it's 750 volts at, I believe, 425 milliamps. Those bulbs would work on 120 volts, but they wouldn't start correctly. They would probably not start at all at that. But if they did, eventually they would draw too much current and just melt themselves down. So what this does is it steps it up to starting voltage. When it gets there, when they get warmed up, it senses it drawing more wattage as it gets warmer and more light goes out, and it starts stepping down the amperage that it uses. How it does that, it's got transformers and capacitors and all that. It says high power factor, probably has a big old capacitor in it, but we're going to dig into that and see what she do. You can tell they're old. These have, I'm not sure on an exact date on these. Got a little rust on her. Right there you can tell. When I took them down, there were stains up in the casings, and later figured out that's tar. They pot these things with tar to reduce vibration and 60 hertz hum. If you've ever been around them, you know, you walk in, one's going out or flickering in these tubes, you can hear this hum they put out, and it will drive you insane. Well, that's what happens. These transformers burn up, they start humming, they get hot, this potting material, this tar leaks out, and that hum becomes more evident because instead of it being around the innards and dampening that, it just throughputs to the case and, like I said, just drives you absolutely insane. But it's enough talking. Let's dig into her. All right, zoomed in a little bit here. Slide good where I'm at, I guess. Zoomed in, you can see first off, it's got the wiring diagram on it. That shows your ballast there, your two lamps. There's red and blue. That are these two wires. One would go to one lamp there, one would go to the other. Of course, up in the wiring to the tombstone connectors in the bulb casing. On this side, so you've got line voltage there, labels it as black and white, but you also notice they go into the ends of the bulbs themselves. So line voltage is part of the circuit, probably more than likely part of the starting circuit there. You have black and white into the other end of them tubes, black to blue, white to red. But you would also have your line current, your 120 volts on this model tied into there. A lot of industrials, 277. A lot of the newer ones are rated for 120 volts to 277 volts. This is not one of them. Not sure exactly how old it is, like I said. But this is just the 120 volts at 60 hertz model. Shows the line current draw of 1.34, so like under an amp and a half draw. Output voltage is 750 volts. That is probably closed circuit, probably what, when the lamps are connected and functioning, what they are drawing. Open circuit without bulbs, say you took the bulbs out or both bulbs failed or something like that, I would probably expect to see 1.5 to 2 kV on it. I'm not sure on these. I really don't mess with AC energy that high. I don't get my fingers nowhere around it. Lock it out and do it. If it works, it works. If it don't, we go from there. That's getting into arcing territory, and arcing is no good. But yeah, 120 volts, 60 hertz, 1.34 amp draw at 750 volts output. Class P automatic resetting thermal get my words together here. Automatic resetting thermal protection, which means if this thing, like we've seen the leaks on it, if it overheats, it's going to cut itself off until it cools down, and then it's going to reset itself. It's probably some kind of simple thermostat circuit in there that when it senses a certain temperature, it's going to open that circuit and stop flowing electricity for safety. You overheat it, tar's, well, I don't know why they potted it with it. Tar's kind of flammable. It stinks when it smokes too. It's just a safety feature with it. But yeah, no PCBs. It's going to be just straight point-to-point wiring, I guess. There's no, it's probably built before the common use or the use even of semiconductors and microcontrollers and all that good stuff. Made in the USA. I noticed up here under their logo, Paramus, New Jersey is where, don't know if I can say it on or not, or even show it really. Guess I'm going to find out. It's where this company's from. Yeah, that's it. It says it takes minimum starting temperature of 50 volts. What that is the current at which 750 volts at whatever I said, 425 milliamps can pass through these tubes. These, you know, the long glass light tubes, fluorescent tubes, are vacuum. They have a vacuum pull on them, and they are filled with, not filled, they have mercury in them. And what happens is when these start up, they're cold. That mercury is solidified. Therefore, they don't have much to conduct in them. It takes a large voltage at a larger than average current to start them. Once they start, once that arc gets, you know, across the bulb, that mercury starts to vaporize. What happens with that is, it's like boiling water. It's steam. It's mercury steam. Mercury, being a metal, is conductive, so that steam is conductive. As that steam fills up this tube, this lamp gets more and more conductive, less and less resistive across these 2 points. You could think of it as 2 wires. Of course, this isn't correct. This is the red and blue, but just for political, electronical correctness here. Between these 2 points starts conducting electricity easier, so you need less voltage and current to run across these to create light. As they warm up, as they start functioning properly, this senses it and steps that down to the 425 milliamps. But, of course, like I said, you have to have a minimum of 50 degrees Fahrenheit to start it. Here's talking about the tar potting material, sound rated C. I'm not entirely sure on sound ratings, but I guess that's good. It's filled with tar and asbestos. I probably ain't got asbestos in it. I said a touchy word there, but you know. It's filled with stuff that there's better stuff to do it now. You can, not sure if you can see that or not. Yeah, we're in frame right there. You can tell where it's leaked out there. Got some nuggets over here. All that. Get the other one here. It's a little less scratched up, but you can read it less on camera. UL listing includes two 60-watt, 8-foot T12 slimline lamps. That's what I took these off of, was F96 T12 8-footers. Lamp current 440 milliamps. Minimum ambient temperature of 60 degrees Fahrenheit. So that would be the running. It would start at 50, but it wouldn't run well. It would suck current and all that, and it just wouldn't be good. Yeah, it's got all your listings, the Underwriters Laboratories, CSA, all, you know, it's good stuff. It was made well. Well, I guess now we're to the point where we open it up. I don't know how I'm going to do that. You can kind of tell. Get it up in the lens here. There. You can tell it's got a bottom case on it, but these have been kind of boogered over, kind of floured out like a rivet almost, but it's part of this bottom case. Yeah, I noticed this on this one. I'm not sure if that's a spot weld. I'm thinking it's where something arced through accidentally, or something shorted out on it. It's a little hole, and you can tell it's gotten hot. Either something very hot or something very energized came in contact with it and melted a nice little hole in it. But it does look like a spot weld too, so there's my reason for tearing it up, to investigate that. Well, let's get them open. I'll probably take the Dremel tool to that. There's 4 of them, one on each end, and might have to heat it up to get that tar to release, but that'll be fine. We can do it. Alright, went and got the safety squints out of the truck here. Safety second or third or fourth, or however you prefer it. See, got the ballast, got the Dremel. Do it to it. Alright, won't record the whole thing, but this is what I'm doing. Taking it, just dishing out that little flowered spot there. And maybe we can get it off after that. Alright. Got her all nice and ground off here. Some basic tools. Of course, in Knipex we trust. Nice German water pump pliers. Got the 6-in-1. Got the Stanley 100 Plus nut buster here. And I'm set to take anything in the world apart. See what we can do with this. It should, I believe, just, yep, crackling, she's popping, she's off. And apparently I have more work to do. That's that tar I was telling you about. And it is full. Yeah, that's tar. You can tell it is in there. Shiny too. I wonder how soft that is. Let's see. Yeah. Ah, hey, we got wires. Okay. There's not too much in there, but it needs something else. Let me figure out, do some Googling, and figure out how to get tar out of a case. Probably some kind of solvent or something like that I could use. Alright, so I'd cut the camera off at this point, but then I found something interesting. I can peel this case off of it. This metal around all this tar. Yeah, it's just gonna pop out. Right there. Well, we got some kind of cardboard on it. Ooh. Hey, here we go. Here we go. Let me cut you off a second and clean her up. But that looks like our capacitors and transformers and all that. Hey, move, cat. Okay, so digging into it, got the pot material off. Sadly, this broke off. This is what I think. I mentioned a big capacitor section. Apparently it doesn't have a big capacitor section. I think that's what this is, though. It's probably a series of smaller capacitors or a smaller, larger capacitor. But I noticed this. That's glitter. That's copper and silver colored glitter. And I don't know what it's there for. So if one of y'all could drop me a comment, or somebody that knows about these things or the history of them, and tell me why there's glitter in it. That blows my mind. But I'm still getting all the potting off of it, and yeah, we'll go from there. Alright, got you zoomed back in here. We got all the potting material off of it, and that was a pain, but it is exactly what I thought it would be. Pretty much what we got here is this kind of section here. That is your step-up transformer. It takes 120 volts line voltage and transforms it into, presumably, from what the case is marked, right here, transforms it to 750 volts. How does it do that? Well, how a transformer works is you have a small coil of wire and a big coil of wire. You get a primary and a secondary. Your primary is always kind of your smaller coil, your less in physical length coil, has less wraps on it. Your secondary is a larger coil, has quite a few more wraps on it. Put voltage in on the primary, it makes a magnetic field, which is why these are called magnetic ballast. They work on magnetism. 120 volts goes in the primary, makes a magnetic field around this iron. This is an all iron kind of, I don't know if you can see the laminations or not. The camera will focus. There we go. You might can see them. It's little laminations, little slivers of iron around this, and there's going to be also an iron core up the center that runs in the center of these both coils, actually. That is what this represents in drawings. My drawing is horrible, but anyways, it makes a magnetic field that energizes that core. Well, pass current through a coil of wire, it's going to make magnetic energy. If you pass a magnet through a coil of wire, it's going to create electrical energy. That's where this transforms, is this small coil of wire is putting out a field, but this big coil of wire is picking it up. Think of it like, kind of like a pulley. I've actually drawn that out here. If you had a motor that ran 120 RPMs and you wanted it to turn a load at 750 RPMs, the way you would do that is you would have a big pulley on the motor and a smaller one on the load. Kind of inverse. In electrical, you have the small pulley on the line and the big pulley on the load, speaking as far as coils, but it's the same concept with it. You can calculate kind of the ratios of turns the same way. I did this, 750 divided by 120 equals 6.25 to 1. So for every, over here on the transformer, for every 1 volt that goes into your primary, theoretically without losses and all that, you would get every 1 volt that goes into your primary, you would get 6 1/4 out on your secondary. So you put, same logic applies, you put 120 in on your line, you're going to get 750 out to your load. That's how it does that. We have in here also, so this takes in 120 volts. Scoot you up where you can see there over the side a little. Takes in 120 volts on one side, turns it to magnet, puts it through another coil of wire, and puts out 750 volts. And that is just from here to here. What are these two? These two are chokes. A current choke. It doesn't do anything to the voltage, just the current. AC, any AC, radio, household 60 hertz like this hates to go around a coil of wire, an inductor. It starts interfering with itself with magnetic fields and all that. What these are is kind of the same thing as the transformer. Draw two legs here. This would be, say, coming off the transformer. Scoot it up where you can see it again. Weird angle. So you got 750 AC coming off of these two. Well, what these chokes are is just a single coil of wire by themselves. And it will pass voltage, but not as much current. It chokes. That's what they're called. It's chokes. As this electricity passes through it, it gets harder and harder to push out. So the max you would get, according to this over here at the actual outputs, these would be your red and blue outputs from your two lamp leads. The max you could get would be 750 volts, but because it has that choke, you're only going to get a potential of 450, I believe. We'll just use that. That's a nice round number. 450 milliamps. So your voltage stays the same, but your milliamps go way down. What that does is that controls, once it gets started and all that good stuff, it keeps your bulbs from overheating. It makes the unit more efficient. It's just a more controlled environment. They're designed to take that, so that's what they get. You can manipulate the length and the size and the size of the coil and the wire size and all that, and get different values. But those bulbs are designed to run with, like I said, let's see here, 425 milliamps, close enough. But that's all that. This big thing that weighs like 8 pounds is coils of wire. That's all that is. Coils of copper around an iron insert. You can tell I kind of tore it up getting it off. You got different outputs, different leads. We got a little capacitor right there on the input just for power factor kind of stuff. That's that. There's your inputs that run to the primary. All these, got two here and two here. This is all going to be outputs. I believe, like I said, I tore it up like an idiot, didn't know what I was doing. And those were all bonded somewhere in there. Got to see solder, all that. As advertised, no PCBs, no digital printed circuits, all this. It's all just wrangling electricity by its weaknesses. Let's see. Move our Alabama fine china out of the way here. Get a fresh one that's under it. The little box I thought was a capacitor. I'm still not sure. It favors a capacitor, but it's got a hole in the center that I don't know what it does. I'm thinking maybe this is a big wire wound resistor. I mentioned in the beginning the open circuit, closed circuit voltages on it. Closed circuit would be when the bulb, like I said, when the bulbs are attached to it and functioning properly. Man, I'm bad with words today. That it would put out 750 volts. Well, if you removed that and this transformer was still running, you would have buildup. You would have just magnetic buildup and voltages just spike. I'm about to test this and figure out what it is, but if this is a resistor, it would keep that voltage buildup from happening. It gives it a constant load across this resistor to keep that buildup down. Actually, let me do that right now. Got the handy digital volts ohms meter here. Maybe you can see it. There we go. And I'm going to go 20k ohms range, 20 kilo ohms. I might actually try to dig into that, show you the inside of one of them. But, yeah, that's it. See if we can get into this. Mark it on the calendar. This was the day I was wrong. That is actually a nice cardboard cord capacitor. It is just layers and layers of shiny metal coated, I don't know what exactly that is. Looks kind of, I don't know, mylar, metal coated mylar. Something as a dielectric, and then it's got a coating of metal on it. And it's kind of like the cells in a battery. They store energy, but they also don't like to see changes in energy. It's kind of a balance thing between them. They resist the change of electricity. If they're charged to a potential and they see a drop, they're going to want to discharge to make up for that. It's kind of a smoothing thing. Probably keeps the flicker rate down where it doesn't look like the light's flickering. Probably a smoothing thing, probably, like I said too, a balancing thing. It's some sort of plastic in between it though, because when I hit it with that Dremel tool, it, like I said, safety first, it sprayed hot plastic everywhere, and I got a fairly good coating of it. But yeah, I was wrong. That is a capacitor, and it's just a very, this is 2 or 3 layers right here, a very thin piece of plastic with a very thin conductive coating on it, and it's wrapped around that hundreds, maybe thousands of times to give the proper capacitance to help smooth it out. Huh. Okay, here we go. That. I kind of peeled it weirdly here. It'll focus right, well, dadgummit. Right there you can see where the layers focus. Come on. For me, please. Well, anyways, you saw it. The layers, hey, there we go. The layers have ripped differently, and you can tell where each layer is. So, continue pulling. There we go. Yep. Right there is one layer, and you can kind of tell. There we go. Where that metal film has stuck over time. That may have been arcing at some point. It arced between layers. That dielectric failed and it arced and vaporized that metal. But yeah, that's like a, you ever looked at the inside of a chip bag, like a Doritos bag? That's that's what this is pretty much. It's metal coated plastic, or some sort of oxide coated plastic. And it acts as a battery and a smoother. It acts as a capacitor because that's what it is. It's a capacitor. Who knew? Alright, so quick little recap on what we touched on, how it works and all this. And we'll shut this one down. You've sat through a 30-minute video and listened to me babble, so I guess it's about time to end it. What we found in tearing it apart, first off we have our step-up transformer. That takes, like we said, the 120 volts AC, converts it to 750 volts AC through a step-up transformer. It then sends it there through the two chokes. What those are, it's kind of like a transformer, but it's not. It's a coil of wire. AC hates a coil of wire. It gets harder to push AC through it, so by the end, down here, post-choke pre-capacitor, you're only getting a maximum of 450 milliamps, so you don't melt down your tubes, overheat them, blow them up, you know, bad things. Down here, my crappily drawn little capacitor symbol, but you get it. Goes between both the hot and the neutral legs of this AC to increase power factor, as I learned. Makes it more efficient, gives the amp draw peak and the sine wave peak, gets them closer together so that it's more efficient. It's a high power factor, has a high power factor to use energy more efficiently, more or less. It does that, and it's also a smoothing effect where your lights aren't pulsating at 60 hertz. It gives it a more stable, it lessens the sine wave of it. It gives it a more stable, less flickery light. Out from there it goes to your lamps and then back to its respective hot and neutral. That's about it on it. I hope you learned something. I know I certainly did, and I really enjoyed it. I will say it doesn't fit back in the case quite like it did before. It's kind of confetti-esque right now. But hope you enjoyed it. Hope we can find something else to tear apart soon. And man, like it, subscribe it, comment on it, tell me what I need to do better, what I need to do in general. Tell me what you want to see us tear apart next. That would be awesome. This channel will only be as successful as the people who watch it, and I don't know, y'all seem like successful people out there on the internet, so let me know what you think. Thanks.